Okay, calculus folks, here is a warm-up for today. You've got, I think you have a handout, and I'm hoping that whoever's babysitting you there will pause this video for a second, give you maybe, I'd say 5 to 10 minutes to try this warm-up, and it's basically a calculator exercise and remembering some stuff about sequences, some notation, and then I'll take it up quite quickly and then get into the lesson that's titled The Limit of the Function. So please, babysitter, supervisor, whoever, please pause the video right now to allow the calculus students to try the warm-up. All right, I'm going to take up this warm-up, and this essentially was a calculator exercise, but the idea is we've got a pattern, and the pattern looks like this, and you just use your calculator and evaluate, and hopefully you got these values. It says write an expression for the general term n. Well, the general term, basically what's changing is that thing and that thing. And so then the nth term, Tn, is equal to 1 plus 1 over n, all to the exponent n. That's the general term. Then it says calculate c at 1,000, c at t of 1,000, which is a way out there term, to the exponent 1,000, and you get a value that's very, very close to 2.72, and lots of decimals, right? Blah, 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 blah. It says write a limit expression for this. So what the heck does that mean? Well, when we go from 1 to 2 to 3 to 4 to 5 to 1,000, we're sort of letting n get as big as we'd like. So it's kind of like this, isn't it? It's the limit, and this is part D, as n, not x or not h like yesterday. N goes to infinity of 1 plus 1 over n to the exponent n. And you might not recognize this number. We haven't seen it very often, but this is a special number in math called e. And e is around 2.72, and it goes on forever and doesn't end. And this is this is one of the several definitions of what e is. The second one's pretty boring compared to this one that ends up with a nice new number e. It's just another sequence, and you write some terms and end up evaluating T20. 3 over 2 to the exponent 20 is this awful decimal, and that's pretty close to 0. So when n is getting bigger and bigger and bigger and bigger, the limit as n tends to 0, this bottom thing gets big, which makes the entire thing be closer and closer to 0. So this limit evaluated is just 0. The next one's was pretty nasty. Right? Nasty expression, but essentially what we've got, 2n minus 1 is just an odd number. So we've got 4 times a power of -1. So this is either going to be -1 or +1, right? So this just changes the sign back and forth. And on the bottom, 2n minus 1 is an odd number. So hopefully when you wrote out the first few terms of the sequence, you got things that looked like this column. And there's my work. You see that? Check some of your work. I don't know if you would have got this pattern, but this B is, the second part is to evaluate the sum, and that's, although it's not written very nicely, it's supposed to be the sum of the first n terms. So the idea is the first term's sum is just 4 because it's just only the one term. And then when I get S2, I add up the first 2 terms, and I get about 2.7. I add up the first 3 terms, and I get about 3.5. And then add up the first 4 terms, and I get about 2.9. It seems to be jumping back and forth. 5 terms, 3.334. If I keep doing this forever, and that's the idea of this limit, keep doing this forever, what do I end up? Well, it's jumping back and forth. We could guess, but it is pi. This definition, where we added up all of the terms in this sequence and let n go off to infinity, the limit of that is equal to pi. So that's, wow, that's pretty cool. Again, if you don't have the second handout, the limit of a function, I'll ask whoever's supervising to pause the video so you get the handout. And the handout is on a note called the limit of a function. And this is actually some quite challenging material that we'll cover, but kind of do a sloppy job of it a little bit. And I'm going to even leave some of the story for this for next class. This notation, the limit as x approaches a of f at x equals L, means that the value of f at x, and then we're going to fill this in. This idea of a limit, and you don't have to write this down, there's a picture that's a decent picture. If this is y equals f at x, the whole idea is that when I am getting close to a, am I getting close to some value L? So a is, I'm getting close to a value of x. Is the output getting close to L rather than something weird happen like having a big gap in there, or a jump function like you saw in like a asymptote like you saw in advanced functions or in grade 11, that sort of thing. We don't want that to happen. And so how do we define what this limit of a function is? What it means is exactly what we just what we'll see here. Whoops. Means that the value of f at x can be made arbitrarily close to L, no matter how far or how close I want to get. Arbitrarily, let me write that out so you can spell it. Arbitrarily close to L by choosing x sufficiently close to a, but not equal to a. So the idea is that if I want to figure out some value close to L, an output that's close to L, it means I'm going to have to pick an x value pretty close to A. And I will explain this a little bit more next class. But if we continue, the one fact that we'll use a lot is, one of the ideas is, if I'm getting close to A from this direction and getting close to A from the right, that if I'm sneaking up on the same value rather than something like this, right? If this is A, well, where would my L be? Would it be down here or up here? This can't happen. This limit doesn't exist, is what we would say. And there is a very sort of clear but difficult definition of this, and that's what I'm going to talk about tomorrow. So let me just fill in these blanks, and we'll hopefully get onto an example that will help. The limit as x approaches a of f at x exists if and only if, now that means something important in math that we'll talk about somewhere along the line, if the limiting value from the left equals the limiting value from the right. Okay, that is, the limit as x approaches a from the left of f at x, and this is what we call the left-hand limit. As I'm approaching the function on the left, this is called the left-hand limit. That this value equals the right-hand limit. And you see how I determine, just by the notation, the difference between left hand, minus, because that means a little bit to the left, minus, and a plus, just a little bit to the right, and that's equal to some output L. Okay? And they have to be equal. I can't have that broken thing going on that I drew earlier. And so when we have the left hand limit equal to the right hand limit, and it's equal to some value L, we say that the limit exists, and it's equal to L. And this is kind of weird enough, but there is a pretty what's called rigorous definition, and this is the story. There's a story that goes, big story that goes along with this, and I'm going to save that till next class. So we're going to skip all of this business, about these symbols, that what the heck does these symbols mean. We're going to skip that for right now. Don't do that because we'll come back to it tomorrow. Let's skip to an example. All right, I'm gonna pause the video here, and just because they don't like having videos that are more than 10 minutes or so, and then pause the video, and then we'll pick it up in part 2 with the next 10 minutes. Okay.